Welcome to The Explainer. Today, we're diving into some massive AI news that is going to fundamentally change how you think about training your models. We're looking at a fascinating new paper called Beyond Backbone Backpropagation. And look, if you've ever stared at a progress bar during a fine-tuning run, just doing the math in your head on how much cloud compute budget you're burning through, this is absolutely the breakthrough you've been waiting for. It promises to drastically cut compute time and CO2 emissions in transfer learning. So let me ask you something. Is your current approach to standard transfer learning actually just wasting your compute? If you're a developer relying on end-to-end backpropagation methods right now, you might literally be eating up your resources, draining your budgets, and totally bottlenecking your iteration cycles. But as we're going to see today, it really doesn't have to be this way. Here is our quick roadmap for today. First, we'll cover the transfer learning bottleneck. Second, we'll unpack the decoupled optimization strategy. Third, we're diving into the benchmarks and CO2 impact. And finally, we'll wrap things up with a practical developer implementation guide.
All right, let's jump straight into Section 1, the transfer learning bottleneck, and the high cost of training.
We really need to talk about the stark contrast between standard methods and the reality of domain shifts. On one hand, standard end-to-end backpropagation forces you to compute full gradients across thousands of convolutional or attention layers for every single training epoch. It scales linearly with model depth, which is brutal. But on the other hand, think about the reality of domain shifts in transfer learning. Often, moving from your pre-trained data to your new target data really only requires minor normalization adjustments. Standard fine-tuning forces your model into these entirely redundant weight updates. Honestly, it's exactly like rereading the entire textbook for every single pop quiz when all you actually needed to do was just skim your notes. It's a massive waste of compute on feature extraction that you've already done. Because of that linear computational overhead, developers are hitting severe constraints every single day. We're talking about extended training cycles that just completely kill your momentum, not to mention the disproportionate energy consumption that is both financially and environmentally costly. If you're working on a fixed budget, rapid iteration is practically impossible. And if you're trying to do clinical prototyping or, say, deploy on edge devices, full end-to-end backprop is often a complete non-starter.
Section 2, the decoupled optimization strategy and pre-computing features.
So this is the real aha moment of the paper. The decoupled strategy is basically a training pipeline that bifurcates, or splits, the optimization process. It totally separates the heavy lifting of feature extraction from the much lighter work of classifier optimization. Instead of re-extracting features every single epoch, you pre-compute the features exactly once. Going back to our textbook metaphor, this is like taking brilliant, super comprehensive notes one time and then just studying those notes for the rest of the semester. You completely eliminate the need for all that repeated, heavy computation.
Let's walk through how elegantly simple this actually is. In Phase 1, your heavy pre-trained backbone processes your entire dataset in a single forward pass. It extracts all the features and caches them. And boom, that's it. The backbone is done. Then, in Phase 2, the magic happens. The normalization layers, like batch norm or layer norm, and the classifier head are trained independently using only those cached features. Your optimization landscape instantly simplifies from this massive, deep learning mountain into the gentle slope of a shallow network.
But wait, if we freeze the backbone, how do we keep the accuracy high without backpropagation flowing through all those deep layers? Well, that leads us to the researcher's secret weapon, a margin-based weighted loss function. You see, standard categorical cross-entropy loss just isn't quite enough when your backbone is frozen, so this margin-based weighted loss supplants it. By incorporating a decision boundary margin, it heavily penalizes confident misclassifications. This essentially forces that shallow classifier head to learn much tighter decision boundaries all on its own, without relying on any gradient signals from the frozen backbone to fix its mistakes. And practically speaking, this allows you to really crank up your learning rates during head optimization. You get faster convergence without destabilizing your features, effectively reducing class ambiguity.
Section 3, benchmarks and CO2 impact and the real-world evaluation.
Now, theory is great, but does this actually hold up? The researchers definitely didn't take any shortcuts here. They evaluated 4 standard CNN architectures, from ResNet 18 all the way up to DenseNet 121, plus 3 vision transformers including VEAT and SWIN. And they tested these across 3 highly complex medical imaging datasets: brain cancer MRI, BRACHIS, and patch chameleon. The results? The decoupled approach consistently reduced the required training time. The accuracy trade-offs were completely marginal, and fascinatingly, several of these decoupled configurations actually matched or even surpassed the standard, wildly expensive fine-tuning baselines.
The impact of those time savings is profound. To quote the authors directly, this efficiency translates to reducing CO2 by orders of magnitude, offering a practical and environmentally sustainable solution. By shifting all that heavy computational load to just a single upfront pass, they aren't just saving time, they're massively reducing the energy required to train state-of-the-art models.
Which brings us to a perfect real-world application. Why medical imaging? Well, medical workflows often demand constant iterative validation. You've got data coming from multiple scanner types across entirely different hospital datasets. Repeatedly training full deep learning models in these cost-prohibitive environments is a total nightmare. This decoupled strategy shines brightest right here, where reducing the cost of iteration means you can actually afford to validate your models properly and sustainably.
Section 4. The Developer Implementation Guide and Implementation Steps.
I love this part because it is so incredibly actionable. If you're using frameworks like PyTorch or TensorFlow, here is your exact 4-step playbook. Step 1, load your pre-trained backbone and freeze every single weight except for the normalization layers. Step 2, run a single forward pass across your training dataset and cache the output tensors. Step 3, rip out your standard classifier head and replace it with the margin-based weighted loss configuration. And Step 4, just train the head and those normalization layers using your freshly cached features. It is incredibly straightforward.
Now, before you rush off to start coding, we do need to talk about memory. Here are the rapid-fire caveats you absolutely must know. While your VRAM consumption will drop drastically during the actual training phase, your memory overhead is going to spike during that initial caching phase. You need explicit cache handling. If you're extracting features for large vision transformers like VIT or SWIN, the intermediate tensor shapes are huge and can easily exceed standard GPU memory limits. So watch out for out-of-memory or OEM errors. The fix? Just implement a disk-backed cache or use memory-mapped arrays, and then load your features in batches.
Another crucial heads up, stay alert during validation. Medical datasets like Patch Chameleon and Break Hiss often exhibit severe class imbalance and domain shift. While the margin loss is a lifesaver, you can't just set it and forget it. You've got to closely monitor your validation metrics during that head-only training phase. If your accuracy dips, be ready to adjust your margin hyperparameters or increase the weight distribution for your minority classes.
But here is the massive payoff for your data science team. Standard fine-tuning hyperparameter grid searches can literally take days. But with the decoupled strategy, because you've simplified the optimization landscape so much, you only need to tune the learning rates and the margin weights for the classifier head. You are shrinking your search space from days down to a matter of hours. That is an absolute game changer for developer productivity.
For those of you who want to dig into the source code, check out the exact dataset splits, or read the full preprint, here are the details. The paper is by Daniel Villacruz, Laura Moran-Fernandez, and Veronica Bolon-Canedo, submitted in June 2026. You can find it on arXiv under identifier 2607-13043.
One final practical pro tip before we close. This method is heavily optimized for prototyping speed and energy efficiency during training. It's not necessarily designed for real-time inference latency. So be sure to validate the caching step against your specific hardware setup and definitely measure your baseline training time against this decoupled approach, so you can precisely quantify your own compute savings. Which leaves us with this final thought. We've seen how decoupling feature extraction can slash your iteration time, maintain your accuracy, and cut emissions by orders of magnitude. So, as you look at your own AI pipelines today, how much compute, budget, and CO2 could your next training loop save? Thanks for joining this explainer, and happy optimizing.